minus 6 minus 4 minus 2, 0, 2, 4, 6 is going to be countable? Yeah, in fact, you could use this idea and this idea, a combination, right? Yes, question?
Can you just say if a set is a subset of a countable set, that it has to be countable?
Ooh. Excellent, excellent. Yes, you can. In fact, that's a theorem that we are about to show. Perfect segue. Awesome. Every subset, not every subset, but every infinite subset of a countable set is going to be countable. That's actually a very helpful lemma because it means that you can avoid doing some of these explicit constructions. So here's a theorem. Every infinite subset of, let's call it E, of a countable set is countable. So let's call the countable set A. Okay, well, what's the basic idea? I'm just going to give the proof idea. It's written out carefully in the book. But what's the idea? The idea is, let's suppose that A is countable, so I will think of this as a sequence, x1, x2, x3, dot, dot, dot. And now I'm picked off various a subset of this. Maybe this is in the subset, maybe this one is, maybe this one is. Skip a few, maybe this one is, etc. Right? But not necessarily everything's in it. But it's infinite. What can I do? Your task now is to list the things in E. How will you do that? Well, sure, it'd be nice if I could like pick off the first thing here, the second thing here, the third thing here, right? So if you take a look at what's happening in the book's proof, this is exactly what's happening. The idea is we're going to, let's let n1 be the first index that appears. So take the infimum of all the indices I such that x sub I is in E. That's n1. Why does this infimum exist? Why is it, what do you mean it's bounded below? Sure, real numbers can be bounded below, but not have a smallest element. This is a set of natural numbers. The natural numbers are well ordered, so a non-empty set has a least element. So this exists by the well-ordering principle for the natural numbers. Okay, you can pick the smallest thing. Now, once I pick off this index, that's the first thing in my eventual thing here. The first thing is x sub n1. What should x sub n2 be for my set E? What should x sub n2 be? It should be the next thing, which in this case is the third element of the original set. So that's what I want n2 to be. In this case, I want it to be n3. So what should I pick off? Steve?
Well, you could make it just the same definition as
Excellent. Let's demand that I be xi drawn from x sub all the x sub I that are in E, but now we'll demand that I be bigger than n1. Okay. And in general, you could demand that n sub k be the same definition and demand that it's bigger than everything preceding it. Okay. And then we have a listing for E. This is the idea. Okay. Happy with that? Beautiful. So this lemma actually will become very, very useful. Because the next question we want to answer is, let's see, we've shown the natural numbers and lots of interesting subsets of them are countable. They've shown the integers are countable. And in fact, then, any subset of integers is countable by this theorem, yes? Good. So what's another set you know of that's likely not going to be finite, and we wonder if it's countable? The rationals. Are the rationals countable? Q. Is it countable? Why is Q countable?
Because I can make a way to count all of them. Like you can make an order of them so that you'll hit all of them.
Okay, so let's call this a theorem. Q is countable. All we have to do is produce a listing. Okay? And in fact, I'm going to do it the following way. I'm going to write the rationals, if you don't mind, as ordered pairs. Okay? So the ordered pairs, I'll just start with, in fact, I'm just going to do the positive rationals, and you can deal with the negative rationals by using that trick. Okay? But let's just say 1 over 1, 2 over 1, 3 over 1, 4 over 1, dot, 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 yes? And now I'll do 1 over 2, 2 over 2, 3 over 2, 4 over 2, etc. And then the next row I will do 1 over 3, 2 over 3, 3 over 3, 4 over 3, dot, dot, dot. Now, these are ordered pairs of numbers, yes? And if I want, and would you agree that every rational will appear in this array, this two-dimensional array somewhere? Yes? Every positive rational. Yes? So all I have to do now is list them in some order. Would you agree that if I do the following, I start here, and then I proceed diagonally through this picture, like so, zigzagging my way, that I will eventually hit everything in this grid, etc.? Yes? Now you should worry about something, because the way I've done this grid, some rationals what? Repeat. But why is that not an issue? Good. What we've really shown is ordered pairs of natural numbers are countable, and the rationals are just a subset of them where you pick one representative to be in this picture, right? You just skip over the ones that you don't care about, right? You don't care about this because it already appeared the first time. You don't care about this because it already appeared. 2 over 1, 4 over 2, you're going to omit. You can omit as many as you like. The whole thing is a countable set, so any subset is. Are you happy with that? Very, very nice argument. So let me point out, not only have you shown that Q is countable, but we've also shown the following theorem. If A is countable, then in fact A cross A is countable. Yes? Yes. That's correct. Yeah, so this is actually a proof that Q plus is countable. But now, if I wanted to show that Q was countable, how could I do it? I'll use this trick. Put all the positive rationals going one way, the negative rationals going the other way. Yes? That produces a bi-infinite sequence, but that can be put in sequence by now picking 0 off first and then doing this thing back and forth. Are you happy with that? John has asked an excellent question. So the positive rationals are countable, and if you want to show that Q is countable, you can either use that trick, or if you like, I can use the listing make one of these include the negative numbers, one of the numerator to the denominators, and list those in some order. Like, for instance, start this one with 1, 2, 3, 4 all over 1, and the next row with -1, -2, -3, -4 all over 1, and then proceed to denominators 2, 3, 4. Use smiley and smiley is this trick. Okay. Excellent.